This video is going to go over the multiplication principle of counting, which is sometimes called the fundamental principle of counting. We're actually going to skip the warm-up on page 1 for a minute and come back to it. So go ahead and turn to page 2 in your packet. The fundamental counting principle, or the multiplication rule of counting, is just a way for us to count possible outcomes. And the way it works is that we are going to multiply the number of choices in each category. So for an example, let's say we're making a sandwich, and the sandwich can have white bread, or it can have wheat bread. If it has white bread, it could have peanut butter, or it could have turkey. If we have wheat bread, we could have peanut butter, or we could have turkey. So we could do white and peanut butter, white and turkey, wheat and peanut butter, wheat and turkey. 2 choices for bread times 2 choices for topping gives us 4 possible sandwich outcomes. So we're going to fill in step 1. The blank will find the number of outcomes by multiplying the number of choices for each event. Multiplication okay. So for example, it says find the total outcomes possible in a win-lose tournament with 3 games. So for the first game, like if this is game 1, we could either win or we could lose. There are 2 options. In game 2, you could win or you could lose, 2 options. In game 3, we could win or lose, 2 options. Means that there are 2 times 2 is 4 times another 2 is 8 possible outcomes for the tournament. The multiplication rule of counting is supported by tree diagrams. Tree diagrams will show you all the possible outcomes, all 8 outcomes as they occur, and it also gives you what's called the sample space. Each specific outcome in the sample space is called an event. So now we're going to show the 8 possibilities in a tournament using a tree diagram. So we have game 1, we have game 2, we have game 3. Now game 1, we can either win or we can lose. Game 2, we could win or we could lose. I'm doing here also, win, lose. And then in game 3, we could win or lose, win or lose, win or lose, win or lose. So you can see here, this top branch, if I follow it 1, 2, 3, this would be all wins, win, win, win. But if I followed the top branch and then the bottom branch, I don't know, and then the top branch, that would be win, lose, win. This would be win, win, lose, win, lose, 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 win, win, lose, win, lose, 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 win. And again, I'm just following my eyes. I'm just going like here, I'm just going lose, lose. And then if I come down to the very bottom, there's the 3 losses. Okay. So those are the 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes for the tournament. So the bottom question says, what is the probability of having at least 2 wins? So I'm going to look, and here this is at least 2, at least 2, at least 2, no, at least 2. Nope, it's just those 4. The other ones are either 1 win or all losses. So the answer is 4 out of 8, or you could say it's just 50%, at least 2 wins. So let's go back to the warm-up page and take a look at those problems now that we've reviewed the multiplication principle of counting. The first question says, in many real-world problems, you will want to count the number of possibilities. For instance, a sandwich situation. But now we have 4 types of meat, and we have 3 types of bread. How many possibilities or how many choices do your customers have for a meat sandwich? So we have meat, 4 choices. We have bread, 3 choices. And that would be 12 sandwiches. And again, I could totally make 1, 2, 3, 4 meat, like ham, turkey, roast beef, pastrami, and then off each, I'm only gonna do it off the ham, so otherwise it gets really crowded. I could show you wheat, white, wheat, rye. So I have 3 branches here, and then if I did white, wheat, rye, white, wheat, rye. That's hard to say. White, wheat, rye. I have 12 branches total, which represents my 12 sandwiches. Number 2 states a standard configuration for a New York license plate is 3 digits followed by 3 digits followed by 3 letters. Letter A says, how many different license plates are possible if digits and letters can be repeated? Now, I want to remind you that the digits go 0 to 9. Oh, that's a bad 0. 0 to 9, which is really 10 choices for digits. So there are 10 choices for the first digit, 10 for the second, 10 for the third. And then for letters of the alphabet, there are 26 letters of the alphabet. I'm going to grab my calculator. 10 times 10 times 10 times 26 times 26 times 26. Wow, that is a lot. Is 17576. 1, 2, 3. Wow, that's a lot. Okay. Now, part B says, how many different license plates are possible if letters and digits, if digits and letters cannot be repeated? Well, that means for the first digit, there are 10 options, 0 to 9. But then whatever digit I've used, I have to take that out. So now there's only 9 choices. Like, let's say we use 1. Now I can only use 0 and 2 to 9. And then I've used 2 digits, so there are 8 choices. Then when I get to letters, I start with all of them, but then I use 1 letter and I'm down to 25. And then I use another letter and I'm down to 24. So 10 times 8 times 9 times 8 times 26 times 25 times 24 is 1, 3 different options. Okay. So number 3 on that page says, police use photographs of various facial features to help witnesses identify suspects. One basic identification kit comes with 195 hairlines, 99 eyes and eyebrows, 98 noses, 105 mouths, 94 chins and cheeks. The developer claims that it can produce billions of different faces. Is this claim correct? Well, let's see. We're going to do 195 times 99 eyes and eyebrows times 89 noses times 105 times 74. I think this is going to be a very large number. Let's find out. Yes, it is. I end up with, on my calculator, 1.33, and then there's an E. So that's like times 10 to the 10th, if it's E10. So I want to remind you, that would be like, so if I took the 1.33 and I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and now the decimals here, and I have 1, 2, 3, 4, 5, 6, 7, 8. So let's see, this would be thousands. That would be so there are 13 billion, because right here, 1, 2, 3, 4, 5, 6, this is the million. And so then if that's millions and this is billion, so there's about 13 billion faces. All right. Witness can clearly remember the hairline and the eyes and eyebrows. How many different faces can be produced? So I'm going to go back up to my original multiplication set. And I know the hairline, so that I don't need that. That's now a 1. And I know the eyes and eyebrows, because that's a 1 because I know what they are. So I'm just going to do 1 times 1, because I know those, times 89 times 105 times 74. And I get a much more reasonable under 1 million. So let's go back to some of the examples in the lesson. So everyone go ahead and turn to page 3. A football team has red jerseys for road games, white jerseys for home games, and gray jerseys for practice games. The team uses gray or black pants and black or white shoes. Step 1, find the number of uniforms by using the fundamental counting principle. So first I'm going to say I've got, the first choice I have is jerseys. So for jerseys, I have 3 options. Then I have pants. In pants, I have 2 options. And then I have shoes. And shoes has 2 options. So 3 times 2 is 6. Times 2 is 12 different uniforms. And now it says use a tree diagram to determine the number of possible. So we know there are going to be 12. The jersey colors are red, white, and gray. So we're going to go, here we go, red. We have red, white, and gray. I want you to notice how wide I'm making these because I know I'm going to have 12 at the end. So here we have jerseys. What are my pants colors? Pants are gray or black. So now for pants, I have gray, black. If you write it out once, you can just go gray, black, gray, black for pants. Now we have shoes, and shoe colors are white or black. So we have white, black, white, black. Like the one I just drew, that would be like a white jersey with gray pants and black shoes. Like here, the one I'm about to draw would be a gray jersey and gray pants and white shoes, or a gray jersey and gray pants and black shoes. Okay. On page 4, we have a spinner situation. A spinner is divided into 3 equal spaces, and it is spun 3 times. So here's the deal. When I spin a spinner, it does not change the number. Like every time the spinner has 3 equal places, like 1, 2, 3. So when I spin it the first spin, there are 3 options. The second spin, 3 options. The third spin, 3 options. 3 times 3 times 3 gives me 27 options. Is there a follow-up? Yes, okay. So we're gonna go tree diagram, and I need some space because I'm gonna have to have 27 here. So I'm gonna have 1, 2, 3. 1, 2, 3. 1, 2, 3. And I'm not going to write the numbers. I'm going to do it the first one, and then I'm going to leave it. This is going to get too crowded. 1, 2, 3. 1, 2, 3. Now here I've got 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Now I'm going to have to kind of like branch this down here. 1, 2, 3. And then 1, 2, 3. So like this last one be spin a 3, spin a 1, spin a 3, spin a 3, spin a 2, spin a 1, 2, 3, and then 1, 2, 3 for the 27 outcomes. What is the probability that after 3 spins, you get the same number? So I can look at my sample space, or I can think, all right, I know I have 27 outcomes. The acceptable outcomes, the same number would be 1, 1, 1, 2, 2, 2, or 3, 3, 3. So there are 3 possible outcomes out of 27. Oops, I wrote a 2 there. That's not good. So 3 out of 27 is 1/9. Right, your homework tonight is to complete pages 6 and 7, and the answers will be posted online.